Hello everyone, I'm Paul and today we're solving problem 2300, successful pairs of spells and potions. This is medium and the key for this one is binary search. So let's start. We are given an array spells, an array potions, and an integer success. And we need to return an array of the same size as spells, where each element corresponds to the number of successful combinations between the current spell and potions. Now maybe you are wondering what is a successful combination. And here we have the description. A spell and potion pair is considered successful if the product of their strengths is at least success. So we start here. And if we do 5 times 1, the result is smaller than success. So this is not a successful pair. If we do 5 times 2, the result is 10, which is greater than 7, so here we have 1. 5 times 3 is greater than 7, so here we have 1. 5 times 4 is greater than 7, and 5 times 5 is greater than 7. Here we have 4 successful combinations, so we put a 4 here. If we take 1, we have 0 successful combinations, and if we take 3, we have these 3 successful combinations. So we put a 3 here. And this is the result for this input. Now maybe you're thinking about iterating every possible pair. And this is fine, but the problem is down here in the constraints. We know that n and m are smaller or equal to 10 to the power of 5. And if we iterate every pair, we need to run a nested for loop, and this requires n squared time complexity, and if n is 10 to the power of 5, this is too much. So we need to think about something more efficient. The key observation to solve this is the following. Let's say we take this spell and we are going from left to right in a sorted array. This is the key for this problem. In this case, this is already sorted, but we might get an array that's not sorted. So first we sort whatever we get for potions. And now we are trying every potion from left to right, so we start with 1, and we are checking if this is a successful pair. 5 times 1 is 5, which is more than 7, so this is not a successful pair. We continue. Next we are here and we do 5 times 2, the result is 10, and 10 is greater than 7. So this is a successful pair. And given that this is sorted, this means that this is also a successful pair, and this is also successful, and this is also successful. So we don't even need to check for these potions. Just by taking this pair, we know that we have 4 successful pairs, okay? The main thing here is that we need to find the left bound from which every potion times the current spell is greater or equal to success. And for this we can use a binary search. So now we are running a binary search here, and this is left, this is right, and this is the mid pointer. And we check if the current spell 5 times mid, which is 3, is greater or equal to success, we move the right pointer to mid minus 1. In this case, 5 times 3 is 15, which is greater than success, so we move the right pointer here. Now the mid pointer is here, so we do the same. 1 times 5 is smaller than 7, so we move the left pointer to mid plus 1. Now the mid pointer is here, and 2 times 5 is 10, which is greater than 7, so we move right to mid minus 1. And now, given that right is smaller than left, we end this loop and return left, which is index 1. So now we can go here and add the amount of elements that we have here, meaning 5, minus the result for the binary search, which is 1. And this is 4, so we put a 4 here. And just to be clear, this 4 represents that all of these potions form a valid pair with the current spell. So this is a valid pair, this is valid, and this is valid. Here we have 4 valid pairs, and that's why we have a 4 here. Next we are here, and if we run the same binary search, the result will be 5. And this means we didn't find anything. So we go here and we add the amount of elements here minus the result for the binary search, and this is 0, so we put the 0 here. Finally we have a 3, the result for the binary search will be 2, and this means we can form pairs with these, and these elements. So we add to the result the amount of elements, 5, minus the result for the binary search, which is 2. This is 3, so we put 3 here. Time complexity for this approach will be big O of n, because we need to iterate this, times log m. Remember that every binary search requires log m time complexity, and this is plus m log m. This is because we need to sort this. Remember, this is the first step, and this requires m log m time complexity. So with this in mind, let's go with the code, and hopefully you will get the idea. First, m is the length of potions, and we need to sort this, so potions.sort. Remember that this is very important to use binary search. And now we can build our function for binary search. We are calling this bs, and this takes some spell as an argument. And this is pretty standard binary search. Left is 0, right is m-1, and while left is smaller or equal to right, mid is left plus right minus left divided by 2. And now if potions at mid times s is greater or equal to success, we update right to mid minus 1. Else we update left to mid plus 1. And finally we return left. So now with this function we can say our result is an empty array, and for s in spells, result.append m minus binary search with the current spell. And finally we return result. So this is the entire code. Here we can cache every spell just in case we have repeated values. So this will be, I guess, a little bit more efficient. So let's submit this and see if it works. As you can see, this works and it's very efficient. If you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.